Okay, what do you want to tell us about today, Giles?
I like the flop bit from before.
Put my teeth.
Newton's laws.
Oh, science.
Oh dear. I'm not an engineer. I've got like an A-level sort of, I did access course for university, did Newton's laws years ago. But I think having an appreciation of Newton's laws helps us to ignore some nonsense that we see and to understand our lifting a little bit better. I even forget which 1, 2 and 3 are. Basically the first one is that nothing does anything unless a force acts on it. But a force is acting on us all the time, that's gravity. We've always got gravity pulling us down. So that's the first thing to remember. I haven't got a practical way of, maybe it does count. Well, I'm talking to George here, what me and George was talking about earlier. Sometimes people dip, and sometimes when they dip, the bar comes away from their shoulder and then crashes on them. And people say, you dip too fast. That's not possible. We've got gravity pulling the bar down towards the floor and gravity pulling us down towards the floor. I suppose pulling our knees up will pull us down a little bit, but not really. So any speed that we can dip at, the bar is just going to move at that same speed. Gravity is going to accelerate at its 9.8 meters per second or whatever it is that right? George is looking blank. George had enough of this already.
How dare you?
But I think this is important.
Yeah.
So when you dip and the bar moves away from your shoulders and you're told that you're dipping too fast, that's just not true. You're not dipping too fast. It doesn't mean that slowing your dip down isn't good advice. But clearly, when we dip and the bar moves away, we've put some sort of jerky movement into the bar to get it off our shoulders a little bit, so the bar moves up a bit and we move down a bit. You can't dip too fast. The fastest you can dip is basically to fall, and the bar will fall at exactly the same rate as you fall. So I find it helpful to know these rules, if you like. They're not rules you can break. We don't do laws anymore, apparently, in science, but Newton had laws that you just can't break because he was Isaac Newton and he was right. So that tells you that there's something else going on, and the slowing down your dip actually just makes you dip smoothly. When you dip too fast, you do a little miniature counter movement. So I suppose that is an example of using Newton's first law, that nothing moves without a force acting on it. And we have got a force acting on us, and it's acting on us all the same. It's accelerating us down to the middle of the earth. So you can look at that, and it doesn't mean you don't tell people to dip slowly to sort this problem out, but you know that it's not them dipping too fast. You can even tell people because they're dipping too fast, but at least you know it's nonsense. So I find it really helpful. I think the second law, I get which way round they are muddled up. The last one is equal and opposite reaction, is it? Whichever, it doesn't matter. It doesn't matter. So force equals mass times acceleration is one of them. And understanding that a little bit. Again, we don't have to do calculations and be biomechanists. We can go and find a biomechanist to talk to if we want. It helps to have some appreciation when you're discussing it with these people as well, so you can understand what they're telling you. But force equals mass times acceleration tells me on a practical level that when someone's doing their pulls and they're just moving like that, if they're not moving the bar as fast as possible, they're not producing as much force as they can. And in weightlifting, we want to try and replicate the sort of speeds we get when we're actually lifting a weight. We accept that if we go like 110% pulls, say, on snatch or clean pulls, will be a little bit slower than you would expect to move a weight that you're going to snatch or clean. But if we're not moving them as fast as we possibly can, the mass isn't changing, the weight that we're moving in ourselves doesn't change. So if we change the speed, we change the amount of force we're producing. So if we move as fast as we can and accelerate that bar as hard as we can, then we're producing as much force as we can. And that's the equivalent to a weightlifter a lot of the time of putting more weight on the bar if you're doing deadlifts or something. So it helps me to understand why I'm shouting at someone to move the weight faster. It's because effectively I'm telling them to lift heavier in a sort of way. I'm expecting them to produce more force to move the same weight faster, and then we'll get a better training effect from that. So it helps me to understand why I'm giving people instructions. What about equal and opposite? Oh, my favourite. I was doing a talk about this stuff once to coaches on a British weightlifting thing, and I was talking about equal and opposite reactions. And at the end, the fella who was sort of introducing me said at the end, yeah, so like if the bar swings out at the start of the pole, it'll go over your head at the end, and that's an equal and opposite reaction. Absolutely isn't. Ruined my talk. If anyone took that away as a message, that's wrong. Equal and opposite reaction happens simultaneously at the same time. So if I'm pulling up on a bar, the bar's pulling down on me. And the way I think of this practically in weightlifting, it's harder to think of maybe getting under a bar, but it's the same in the clean and snatch. But in the jerk, when we've driven it, the more force we put into driving ourselves under the bar, the more we also push the bar up. Hopefully we're a fair bit lighter than the bar when we get good at weightlifting, so the bar moves up a bit less than we move down when we push against it. But once your feet leave the ground and you're moving it into your split, because you're probably a split jerker, because that's what you all do, but you've moved your feet in the air, it's like you're floating in space for a sec. And when you push hard on the bar, you push yourself under the bar hard, but you also push the bar up a little bit more. When we get here in a pool, when we pull ourselves under a bar hard, we also get a little bit more height on the bar because we're pulling ourselves down on the bar, which is us pulling up on the bar as well. Did that make any sense? We're pulling us down and we pull the bar up. That's your pair, that's your equal and opposite reaction. So being really forceful about getting under the bar is actually getting a little bit more height on the bar for you and get you under the bar a little bit easier. So we don't want to just pull and drop. We want to pull ourselves forcefully under the bar to get a little bit more, and that's a good example of equal and opposite reaction. We're pulling ourselves down on the against the bar, which means the bar is pulling we're pulling the bar up as well. So I think just having a sort of like, I honestly, it was an eye-opener for me doing A-level standard of physics, and I think it's a great thing that any coach can do. I think that one of the things weightlifting coaches look for qualifications to do to make them better at their coaching. Maybe it's a little bit outside what you'd normally look at, but there's lots of sort of industry things looking at muscles and mobility and different things you can get good at that are all important. But I think an A-level in physics, amazing for helping you understand mechanics and helping you to understand what someone's trying to say about technique and whether that makes any sense. Like getting your knees back, being here over the bar when we're during a snatch or clean pull. If the bar's out here, even if we're balanced a bit, when we want to get that bar back, we pull on the bar to get it back. The equal and opposite reaction is us getting pulled towards the bar. And that's one of the reasons we need to be weighted on our heels here, is so we've got a bit of leverage against the bar and we can actually get the bar back into our hips. So thinking this way just helps you. We tend to talk in details a little bit, and thinking this way just helps you with those details. And I see some, we all look at the internet, and I see there's loads of good stuff on the internet, and there's loads of good weightlifting stuff on the internet. Follow Chris Speed on the internet. I really enjoy his stuff, his mobility stuff. I copy it all the time. He'll be glad I've said that, because about 20 people watch these videos and he gets squillions, but he's great. There's plenty of good people on the internet, but I do see ones that are just egregious and wrong. And it's easy to ignore them when you've got your A-level physics and you can just go, well, that ain't right. Snatch balance. If you drop under a snatch balance without doing anything else, the bar will just drop with you. You have to push up on it. It doesn't mean you have to push with your legs, but if I'm doing that and the bar ends up at arm's length, I've pushed up on it. So we can't just drop, doesn't matter how fast we try and drop. We can't fly downwards. So you can just see things that goes against the laws of physics. it's not a real thing. Some of these things, it doesn't make them not good cues, because what we think and what we do aren't necessarily the same. But it just really helps me, and I think it would help a lot of other people, to think a little bit about Newton's laws, and it just helps you to anchor yourself in the real world and know what can work and what is maybe a good cue, but actually not true. How's that, George?
I'm not sure about the brevity, but I think that's a good starter on science.
Oh, good. Was I supposed to be brevet?
Yeah, you said you were going to be more brevet today.